Good day, ladies and gentlemen. I'm Helene-Marie, and I will be telling you about how I've gone about finding application alternatives for sulfide-enriched coal waste in a way that avoids shooting from the hip and allows and encourages researchers to break out of silos and get input from industry experts and stakeholders. In our case, this has allowed us to seriously consider a surprising solution that we wouldn't have thought of otherwise. The background to our study is that South Africa is still heavily reliant on coal for meeting our energy needs. Just under 70% of our primary energy is produced from coal, but this necessity is not obtained without a cost. Coal-bearing minerals also tend to contain significant sulfide minerals, mostly pyrite, which, when in contact with air and water, in the presence of microorganisms, lead to acid rock drainage generation. Rock drainage mixes with fresh water sources, drastically reducing their quality. This in turn leads to soil sterilisation and health impacts on humans and animals. To address these issues, researchers at the University of Cape Town have developed a multi-stage separation process which separates sulfide-containing and therefore acid-generating fine coal waste into 3 streams. A residual coal stream is recovered, which can be blended and sold into existing channels. A sulfide lean stream is recovered, which can be used in a wide variety of applications, such as construction materials and fabricated soil. The last stream is the stream that my work has focused on, and this is the acid-generating sulfide-enriched stream. I have looked at finding different ways of using the sulfide-enriched stream to avoid land disposal and the associated acid generation risk. To do this, I have appropriated the innovation value chain conceptualized by Hansen and Birkinshaw. It shows the innovation process as one of moving from identification of potential innovations to transferring and implementing them in practice. This ensured that the development process was structured and disciplined, which is often not the case. For the identification step, I did a literature survey and preliminary analysis. The selection step was done by screening out the non-starter alternatives and subjecting the remaining ones to multiple criteria decision analysis. This was done with the help of experts to broaden the knowledge pool and expertise that we could draw from. The development step was a pre-feasibility study that was done to set forth a research agenda, and the transfer step was approached by conducting interviews with various industry stakeholders. The selection and transfer steps, in particular, were conducted in such a way as to cross the university-industry divide and make use of industry expertise. Although these steps look very linear when depicted like this, the reality is very different. An iterative, circling approach is more appropriate to problem solving. For alternative identification, I identified several alternatives, such as sulfuric acid production and iron production, among other options. These were then described by block flow diagrams, mass balances, and market descriptions. To start focusing on the more viable options, everything that would not be possible with a 20% pyrite content was removed from the analysis, since this is still a waste stream that we're working with. From there, the alternatives were analyzed using multiple criteria decision analysis, which uses multiple criteria. I chose to use the classical techno triple bottom line to develop the criteria, since it allows for the inclusion of both technical and economic criteria that are classically necessary for technology development and transfer, as well as social and environmental criteria that will help to ensure that the technologies taken forward won't have worse impacts than the acid rock drainage we are trying to prevent. A few criteria were developed. Among them, the technical maturity of the technology, the expected community health and safety impacts, and the water consumption of the technology. And this was done in an effort to really understand the technologies in a holistic way. These criteria were then used to evaluate the different processing options. As you can imagine, the matrix was quite large at this point. I show the 4 criteria and 3 alternatives here only as an illustration. At this stage, I asked several process design experts to help me with the evaluations, since they are experienced in assessing technologies in the very early stages of design, where there is still much uncertainty. These experts helped us to anticipate the performance of each of our technologies based on the techno triple bottom line criteria. This also allowed us to access a wider range of skills and experience than was available in our context. Information was then aggregated in 3 slightly different ways, and the results are shown on this graph here. Based on the analysis, soil amelioration and cemented paste backfill were the 2 best performing options. These were then taken forward to the development step. When I looked at cemented paste backfill, it became clear that coal mining does not produce enough fine material to make this a viable option. Also, the chemical stability of the solution is not proven, and it may lead to acid rock drainage in the medium to long term. Soil amelioration, on the other hand, proved more interesting. Amelioration is the improvement of a soil's physical, chemical, and nutritional characteristics. Our material is appropriate for the amelioration of alkaline soils. Here is a map of one of the alkaline soils in South Africa as an illustrative example. As you can see, these soil types are located in the dry western parts of the country. Agricultural activities in these areas include grain production, table grape and some fruit farming on the banks of the Orange River, and grazing. The most important coal fields in South Africa are in Mpumalanga and the Limpopo province. Soil amelioration as an application of fine coal waste is promising, but it may not be profitable due to the long travelling distance between the coal fields and the agricultural regions of interest. Also, the safety of the material for agricultural use must be first established, despite initial indications being that metal toxicity should not be a problem. As for investigating transfer, I conducted interviews with industry stakeholders to get to know their perspectives and opinions on the barriers and enablers we are likely to encounter as we embark on developing and transferring our waste valorisation technology. We also asked who the best development partners would be. This was to check our assumption that we would need to approach mines. Industry stakeholders I spoke with were coal major executives, coal junior executives, individuals who have successfully implemented technologies, and consultants to the coal mining industry, as well as coal industry researchers. The interviews were recorded and transcribed and analyzed using thematic analysis. Barriers that were identified included the high cost of upscaling technology from lab to industrial scale, as well as the pressure that the coal industry perceives itself to be under, which is likely to increase the importance of a sound business case. On the enabler side, as expected, a sound business case was considered of utmost importance, as was the fact that the technical viability of the waste valorisation approach must be thoroughly proven, and industry representatives must be able to interrogate the results of any tests. Lastly, the pressure that the legislation is putting on companies to reduce their environmental impact was considered an enabler. As far as who the transfer partner would be, we were surprised. Respondents suggested that original equipment manufacturers, called OEMs here, or boutique waste processors, would be the organizations to approach. This surprised me, since I very much expected mines to be the appropriate development and transfer partners. Results suggest that mines will have to be involved in the development, since they are the waste owners, but they will most likely prefer to outsource any technical functions and the management of small revenue streams to trusted OEMs. This information will inform our approach to technology development and transfer in the future. In conclusion, using the structured innovation value chain approach for finding applications appropriate for waste valorization can help one to consider surprising solutions and break institutional silos. In our case, this has led us to seriously consider soil amelioration as an option, which we would not have done otherwise. Also, based on the transfer work that was done, we now know that further development and implementation of the solution should be done with the help of original equipment manufacturers or boutique waste processors. Thank you. I would like to acknowledge my funders and supporting research groupings.